Marine Gurukul has launched a number of online modules to support the students in passing their competency exams. For more details, you may connect with us and write to us on the email ID on the screen, that is marinegurukul@gmail.com. Thank you. Hello, this video is being released out of turn in the sense that without covering the basics of SF and VM, this video is being released at the request of a lot of students who seem to have some confusion about SF and BM of a cantilever. So we first start by understanding what a cantilever is and how is it represented in a diagram. A cantilever is nothing but a beam. It could be a light beam, beam of uniform cross section, beam of non-uniform cross section, supported or fixed at one point, and usually that is one of the end points. Let's take two illustrations to understand how a cantilever can be represented in a diagram. We have a cantilever given here consisting of a light beam AB 10 meters long supported at its left end A. It carries a point load of 30 newtons at its free end and a uniformly distributed load of 50 newtons over 5 meters from its fixed end. This cantilever can be represented by the support here where it's supported. This line represents the beam AB, 10 meters in length. A is the fixed end. B is referred to as the free end. It carries a point load or a point force is at the free end of 30 newtons and a uniformly distributed load of 50 newtons is placed over 5 meters from its left end. You can see the UDL and the point load both put on the beam, and we have this cantilever which can be represented like this. Let's take another case of a cantilever where it consists of a 10-meter long beam of uniform cross section weighing 60 newtons supported at its right end B. It carries a point load of 30 newtons at its mid length and a UDL of 50 newtons over 5 meters from the free end. So here is the support. This is the beam of uniform cross section supported at its right end B. Obviously B is the fixed end then and A is the free end. The length of the beam in meters as given, weighing 60 newtons at the rate of 6 newtons per meter. At the mid length we have this point weight of 30 newtons, and over 5 meters from the free end we have a uniformly distributed load of 50 newtons which is distributed at the rate of 10 newtons per meter. So through these two illustrations, I hope it's now clear as to how the cantilever given to us in a question can be represented in a suitable diagram. SF of a cantilever. In case of a cantilever, the total reaction, which is equal to the total downward forces, acts at the fixed end. So the reaction acts at the fixed point or the fixed end. That is the point of the support. The rest of the SF process for a cantilever is very similar to that of a simple beam. SF at any point being the algebraic sum of the forces, that is algebraic sum of the downward as well as upward forces to any one side, either to the left of the point under consideration or to the right of the point under consideration. The sign convention needs to be followed to remove the anomaly in the direction of the SF obtained by algebraically adding the forces either to the left or to the right of the point. The sign convention is for forces, if you are taking the algebraic sum of the forces to the left of the point, then upward forces are taken as positive and downward forces are taken as negative. If you wish to calculate the SF by considering the forces to the right of the point, sign convention is reversed. The upward forces are taken as negative and downward forces are taken as positive. The numerical value of the SF at corresponding points of a left end supported cantilever and a right end supported cantilever will be same. However, their signs would be reversed with respect to each other, and are understandably why, owing to the shift of point of reaction. So corresponding points here means free end to free end, fixed end to fixed end, or any other corresponding point with respect to either the free or the fixed end. Let's learn the drawing of the SF diagram of a cantilever through a question. A cantilever 6 meter long carries a concentrated load of 30 kilonewton at its free end and a uniformly distributed load of 20 kilonewton per meter over its entire length. Draw SF and BM diagrams. Now in this question, it's not stated whether the cantilever is left end supported or the right end supported. In such cases, the candidates may take their own call and are at liberty to take a cantilever which is left end supported or the right end supported. The numerical value of SF in both the cases would be same, but their signs would be opposite because the point of application of reaction would change. So let's first take the left end supported. We'll be drawing both so that we can compare and see. So left end supported, we first draw the diagram for the cantilever, which we've already discussed as to how to draw. We have the cantilever supported at its left end, 6 meter long with a UDL of 20 kilonewton per meter and a concentrated load of 30 kilonewton at its free end. The fixed end is named A, the free end is named B. The total reaction shall be equal to the total downward force, that is 150 kilonewton. This entire reaction acts at supported end, that is end A in this case, as can be seen in the diagram now. Now with the diagram of the cantilever done, we shall make the SF table. We can make the SF table with just 2 points, the ends, because it's a simple case. So 2 points are sufficient for us to be able to draw the diagram. We make the SF table for points A and B. We'll go from left side to right side, and when we go from left to right, upward forces are positive and downward forces are negative. SF is in kilonewtons. We divide A and B into 2 parts. Just to the left of A, the shearing force is 0. We carry forward the 0, and as we move just to the right of A, plus 150, the reaction comes into play and the shearing force changes to plus 150. That means the shearing force changes from 0 to plus 150 at point A. We carry forward this plus 50. The change from just right of A to just left of B is minus 120, making the shearing force just to the left of B as plus 30. We carry forward plus 30 and then the minus 30, the concentrated load comes into picture, making the shearing force 0 at B. So as can be seen in the table, at A, the shearing force changes from 0 to plus 50, and at B, it changes from plus 30 to 0. Now we draw the SF diagram. We have the x-axis, this is the beam, 6 meters long, and the y-axis represents the shearing force in kilonewton. We mark point A, the fixed end, and the point B, the free end. We graduate the y-axis, each graduation representing 30 kilonewton. Now we mark the SF forces from the SF table. At A, it is 0, And from 0 it changes to plus 50, represented by the green dots coming up in their appropriate location. Then from plus 150 it changes to plus 30 at B, and then 0 at B. From now we join from 0 at A to plus 150 with a straight line. Now how do we join the plus 150 point to plus 30? We look at the beam diagram and we see that the weight of the beam is uniformly changing, and hence from plus 150 to plus 30 the change is at a uniform rate. That means these 2 points have to be joined by a straight line, and that's how they need to be joined. And then at B it becomes from plus 30 to 0. So this is the shearing force diagram for the cantilever with left end supported. Now we'll go on to see how the same SF diagram would look like when we have the right end supported. We start with making the cantilever diagram with right end supported. You can see the diagram coming up. Again, end A is supported and B is free, so A has gone to the right, B is to the left of A, with UDL on top and the concentrated load at the free end B. The total reaction now at a fixed end A, as can be seen in the diagram. Now we make the SF table for 2 points B and A, and like the previous case, SF to the left of B is 0. As we go to the just right of B, minus 30, the concentrated load comes into picture, making it minus 30. So at B, the shearing force changes from 0 to minus 30. Carry forward minus 30, the change from right of B to left of A is minus 120, making it minus 150. Then minus 150 and reaction at A of plus 150, making it 0. So the shearing force changes from 0 to minus 30 at B and minus 150 to 0 at A. Now we make the shearing force diagram. We have the x-axis representing beam. We have the y-axis representing shearing force. We have points A and B. A is fixed. We have the graduations, each representing 30 kilonewton. At B, the shearing force is 0 to minus 30, the two dots coming up. At A, it goes to then minus 150 and then to 0. We connect them as we had earlier done for left end supported one, and we get this diagram for the shearing force for this particular case where the right end is supported. Now if you see the two shearing force diagrams, at free end on both sides the shearing force is numerically same. At fixed end it is same. At any other point, if you see the corresponding points equidistant from either fixed end or free end, the shearing force is numerically same. Only difference is the sign has changed, and that we can understand why it has happened, because the reaction has shifted its position from left end to right end, but the numerical value of the shearing force remains unchanged. Now let's come to the BM diagram of the cantilever. To draw the BM diagram, BM is calculated at select stations along the cantilever beam. We shall be calculating the BM by integrating areas under the SF diagram. Please pay attention to this point. The BM at the free end of a cantilever is 0. So it is recommended, not mandatory, but recommended, that the BM table is preferably made from free end to fixed end. As the area under the SF curve are integrated from free to fixed end, and sometimes your free end may be to the left, on other cases it may be to the right. So the sign convention must be respected and taken care of. As per the sign convention, if you are integrating areas under the SF diagram to the left of point of interest, then positive SF area will give you positive BM. However, if you are integrating areas to the right of point under consideration, then positive SF areas will give you negative BM. So please pay attention to the sign convention, otherwise you could be making a mistake. Now we shall learn how to draw the BM diagram of the cantilever. We shall be calculating the BM at select stations by integrating areas under the SF diagram. Here are the two SF diagrams, one for the left end supported and the other for the right end supported. We shall be drawing the BM diagram also for both of these cases so that we can see that the BM at the corresponding points is same. Now just for the sake of convenience of shaping the BM diagram, we pick up one extra point midway between A and B in each of these diagrams. We have taken point X here, and SF here would be mean of 30 and 150, that is plus 90. Likewise, we take X out here, and here it will be minus 90. For again, to be able to use swiftly in the tables, we calculate these areas. This area we can call as A1. It's the area of the trapezium, half plus sum of the parallel sides into the distance between them, that is 180, and this area comes to 360. The area out here, this one would be 180 and this is 360. Now please remember the sign convention. If you integrate the areas under the SF diagram from left going towards right, then positive SF will give you positive BM. If you are integrating from right to left, positive SF will give you negative BM. So we'll first draw for the right and supported one. So BM table we shall preferably make from free end to fixed end. Now here is the table. We make it for from free to fixed. So free end in the right supported one is B. So B, X and A. Units of BM would be kilonewton meter. Now area under the SF diagram to the left of B is 0. We carry forward 0 and now we are going from left to right. Change in area from B to X is this area A1 in the negative side. It will result into negative BM because going from left to right, so minus A1. So BM at X would be minus 180. We carry forward minus 180 and then from X to A, the change would be minus 360, making it minus 540 at A. With these values of BM, we draw the BM diagram. You can see it coming up, beam on the x-axis, BM on the y-axis. And we have these points B, X and A. We graduate the y-axis. Each graduation represents 180 kilonewton meter. At B, the bending moment is 0. At X, it's minus 180. At A, it is 540, all represented by the green dots coming up. Now we have to join these points. Now see the SF diagram. We are integrating areas under a slanting straight line. So the BM diagram would be a curve, a suitable curve. And this curve represents the BM diagram for the right supported cantilever. Now let us draw the BM diagram for the left end supported cantilever. We have the end A supported, end B free, and here on the left side is the SF diagram for the left end supported cantilever. We shall make the table again for 3 points, preferably from free end to fixed end. So we make the table from first B, then X and then A. Bending moment will be in kilonewton meter. And now from B we'll be going to X, from X to A. So we are going from right to left. When you're going from right to left, positive SF will result into negative BM. So now to the right of B, the area under the shearing force diagram is 0. Bending moment at B is 0. We carry forward 0. Change from B to X is minus 180. Why? Because we are going from right to left. So the bending moment at X is minus 180. We carry forward this minus 180. Change from X to A is minus 360, making it minus 540 at A. We draw the BM diagram, keeping the x-axis again preferably in line with the fixed end. So you can see the two axes being graduated, and all the needful markings are done. Now at B, we have the BM 0. At X, it's minus 180 and it's minus 540 at A. Like the diagram on the opposite side, these points are, because you are integrating areas under a slanting straight line, they are joined by an appropriate curve, and this is the BM diagram for the left and supported cantilever. What do you see in both these diagrams? The bending moment at the free end is same, at the fixed end is same, at the midpoint is same, at any other corresponding point is also same. Now, this should dispel all doubts in your mind. Why? Because whether this cantilever was left end supported or right end supported, irrespective of that, the cantilever force distribution bending moment concept remains the same. So the bending moment at the fixed end in both cases should be same. At free end in both cases should be same. So there is no reason for the bending moment at free end in two cases to be different, or at the fixed end to be different, or at any other corresponding point to be different. Therefore, please remember, the bending moment of a cantilever is always 0 at its free end. I hope you find the video useful. If so, please share with your friends so that they can also benefit from it. Thank you very much for watching Marine Gurukul video series. Do share your comments through the comment section. Like the video, subscribe to the channel, and activate the notification button. Thank you very much.